好的。Okay, so let's start our lecture today. So, let's say that want to show that these two functions they converge locally uniformly on K, right? So, what is the reason why this Fn converge? So basically, okay. So let's say that okay, so let's try this. So, so can we find some uniform bounds for the infinite product of F? So basically, can we really control this the infinite product here, right? So can we control F and Z basically, right? So basically F and Z is represented as finite product. So let's check the convergence criterion for the infinite product of functions. Okay, so I'm checking the Wikipedia for the convergence criterion for the infinite product. So I think there is a theorem for the real numbers, right? So the real numbers, yeah. But let me see if there is some criterion for the complex numbers. So, okay. Okay, so it says that. Okay, so let me summarize what he said. So okay. So okay. So if the logarithm is something a fixed branch, okay. With the provision that the infinite product diverges when the infinite many a fell outside the domain of okay. So okay. So okay. So okay, so oh, okay. So so there's a formula says that yeah, so it says that if we have it says that so formula so that an is which is equal to 1 plus pn, and then that okay, so the bounds okay. The bounds one plus summation n from 1 to n of pn is less than equal to the equivalent product n from 1 to n from 1 to capital N of 1 plus pn, and then which is less than equal to the exponential of sum n from 1 to n of pn. So if we use this relation, then what happens is that so this relation gives us so this implies that so this implies that so the product n from 1 to capital N. Okay. So basically it's the fnz, right? So this implies that fnz so which is less than or equal to the exponential of negative sum from I from 1 to n of z over omega I. Okay. So does this one converge? Okay. So now the question becomes okay. So yeah. So let's see. So yeah. So we know that so if we look at if we look at its function pointwise, right? So what do we get? Wait. I think I was confused. So I don't think. I think these PN they are like the real numbers. Okay. So. If a product merges with if a remaining also. Okay, so yes, I was a little bit suspicious on this one because because this one is just like a so this one is just like a so this one is just like a let's see so this one is just like a yeah, I think these are like the reals, the reals case. So 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 I think we can so the product so we know that the product from 1 to infinity of an is so convergence if and only if and only if the sum summation n from 1 to infinity the capital log of an converges. So where the logarithm is understood as a fixed branch of logarithm which satisfies the condition that log of 1 is equal to 0. Okay, so okay, so okay, so let's see. So so why if we take the natural log of fn will give us the convergence. Okay, so let's see. So y. So which log are we retaking? So okay, so here so I'm thinking of taking the principal log. So is it possible to take the principal log? Yeah, so Okay. Okay, so let's think of the question where, so, yeah, the question is that, can the principal log works? Works here, okay. So can the principal log works here? So namely, okay, so I think basically to consider the branch. So basically, what's going on is that because for the branch, right? So basically, what we do is that we take the puncture. We take the puncture plane and then we so what do we do for the branch of log? So wait, the branch of log is the local inverse of the exponential map. Oops. Okay. So the log is the local inverse of the exponential map. So, and then for the exponential map, so for the exponential map, okay, so the origin is being punctured out, and also for the exponential map, there's a radius, and then there's an angle, there's a radius. Okay. So which is the branch of log? So let's focus on the points, right? So好的，我知道。Okay, so okay, so yeah, so can the principal? Okay, so for the principal log, so we know that yeah, it depends on how I define principal log, of course. So basically, yeah. So basically, for the principal log, okay, so let's consider what do I need in order to define a branch of log. Okay. So that. So okay, so here we know that. So basically this is like the exponential map, right? And then, so okay, so question, what do we need? To define a branch of log. So okay, so let's call this the plane. Let's call this the W plane. Okay. And let's call this the Z plane. Okay. So basically, okay, so let me check the definition of, so because I was a little bit not sure about the some definition of the log. So from my understanding, the log is the local, it's a continuous multi-value function from, let's say, C star to C, right? The logarithm function is a multi-value function. Okay, so it doesn't say whether the domain is the function plane or something. So I'm guessing that the log. So usually when we say the log, I think the convention is that, yes, okay. Yeah, so when we mention log, I think there's no default setting that the log must be defined on the puncture plane, right? I think the log can be defined on even like any subset of the puncture plane. Yeah, I think basically that would work. Yeah. Yes. So okay. So here, so okay. So what do we need to define a branch of log that which satisfies the log of 1 is equal to 0. So I think my current answer is I don't think it can. Yeah, sorry, I need to take back my words. So I don't think it can be defined as any subset of C, right? Because I think there is always like so for example, if you take the exponential map, let's say between 0 and 2 pi, then when the angle is equal to 0, then you will be mapped into this ray, right? And then when the angle is also 2 pi, they will also be mapped into the same line, which does not create like a inverse function. So so I think there is some continuity issue at if we at this line, right? So namely, if you go like from here to this line, then your values may so the local inverse may be like values here, and then when you approach to this point from the positive side, from the upper half plane to this point, then the value might be just approaching to this point. So there's no way to define the local inverse in a continuous fashion in this way. So I think there needs to be some, at least the puncture, some sense of deleting one ray here. Oh wait, no. Come here. 回来。Okay, so okay, so yeah, so what do we need to define them? Okay, so let's focus on what are these points lies on. So okay. 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 Oh. Okay, so the thing I'm worrying about is that so there's no current answer yet. Okay. So yeah. I think in our example it depends on the missing point. Okay. Not missing point. It depends on the point, because you don't want to, because if you want to define like a logarithm, so maybe you need like a cutting ray, right? From the origin, okay. Because you don't want the cutting ray to be you don't want the cutting ray to be hitting one of these points, right? So therefore, in our example, it depends on the points, like say 1 minus z over omega I, right? Yeah, so you don't want to yeah, so you don't want to hit through any you don't want to just go through any of these points. So yeah, so basically yeah. Okay, so Okay, so I just have an idea here because we know that so also since that uh, because in order to kind of picture what does these points look like in general, right? So basically, and also you want to if we think of the idea that this ray, right, including so this origin must be punctured in order to define the log, right? The origin must be punctured if you want to define the log. So, so, but can one of these points be on the origin, right? So, for example, if z happens to be one of the lattice point, so, but the answer is that if z is equal to one of these lattice point, then you will have one of the product as zeros, right? So that implies that the fnz at the values on this fi is equal to 0. Okay. So that would rule out the condition where this one of this point will be the origin point. Okay. So let's say that. Okay. So okay. So okay, so maybe I have to delete this one, or maybe later I can maybe write off first. So, so since this fnz is equal to 0, for any z which is okay, so we haven't used the condition of this complex set yet. Okay, so for any z, let's say belongs to one of the lattice point wedge. Okay. Oh. Okay. So so we may assume that. Okay, so assume. So let's say we focus on. Okay, so we focus on. We focus on the values. The values. Fnz. Where z is not in the lattice point. Okay. So so namely, namely, oh shoot. Okay. So namely, fnz is yeah. Okay. So the cat is kind of on a retreat right now. So yeah. So okay. So i.e. Okay. So fnz. Yeah. So i.e. fnz is not equal to. Okay. So i.e. Okay. So i.e. 1 plus, so 1 minus z over omega I is not equal to 0 for all I in z plus. Okay. 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 So that solves the 0 issue, right? So I think it is doable because yeah, because I think we can just pick a ray so that avoids all the okay. So uh so uh yeah, so so the idea is that so we can pick. So actually, I think we can pick the lattice point. We can pick the ray. Okay, so so we can pick a ray. Let's say e to the I theta times 0 to infinity that avoids that avoids all points 1 minus z over omega I, right? Where I from 1 to infinity. And the reason for that is so the reason for that is because we know that from this enumeration, right? We know that when this I is getting larger and larger, the omega 1 is like circling around way and like further and further towards the origin. And then what happens is that so when this I is like is large, so I'm using this notation to denote that this I is very, very large. So omega I is away from the origin, right? And so when this omega I is away from the origin, so we know that the point 1 minus z over omega I okay, maybe I think we have to fix the z first, otherwise we cannot really talk about picking a ray, right? Because when the z is like changing, yeah, because this argument basically talk about the pointwise convergence for like a sequence, not a convergence argument for like a general function, right? So I think I think we have to fix a z first. Okay. Let's say okay. Let's say we fix a z. Okay, so this is the very beginning precondition. Okay, sorry, I'm just writing it here. So fix the z. That is not in the lattice point. Okay. So let's say this is our precondition. So so this omega I is away from the origin. So and this implies that okay, so when we fix a z and then when this omega I is away from the origin, so we know that this guy, the modulus of this guy is very small, right? So and then when you so when you have 1 minus a thing that's a point that has very small radius, it will still it will stay close to 1, right? So it's omega is already from the origin. So and this implies that 1 minus z over omega I is close to 1. Let's say that it lies in some disk of radius epsilon or something. We can pick the epsilon to be, as long as this omega I is the modulus of this omega I is very large, right? So that the modulus of this guy is less than epsilon. So yeah, it's close to 1. Okay, so it's close to 1. So yeah, so this means that for all such big I, so we know that these points will always stay within like a small circle, right? And then i.e. so there exists like epsilon bigger than 0 such that epsilon bigger than 0. Oh, let's say that this epsilon is less than 1/2. Okay, and then let's say like n like a very large number, very large positive integer. So such that the point 1 plus z over omega I, 1 minus z over omega I will stays in the disk centered at 1 of radius epsilon for all I bigger than or equal to n. Okay. Yeah, so this is true. And also for I being small, there is only finitely many points, right? So that I can always choose an array that avoid this finite many point, and then avoid this like choose the angle such that this ray just avoid the disk, and then just passing through one of these, any of these finite points. Yeah. So yeah, so we are okay to, after we fixing this ray to avoid all these points, and together with choosing the z that's not in the next point, so then we are allowed to define the branch of log based on this missing point. Okay. And also the missing point is finite. And also the so there are finitely many points. Okay. Many. Yeah. So namely, there are just n, like m minus 1. 1 minus z over omega I that lies outside this disk. Okay. Okay. Yeah, so we are okay with the branch of logarithm. So okay, so let's see what happens if we, so yeah, so let's see what happens after we pick this log. Okay. Yeah. Yeah. So let's see. So how do we really pick the log? No. Sorry. How do we really yeah. So let's see what happens. So Okay, so maybe I just delete this one. So so first pick the logarithm according to the ray we derived. Let's denote this mechanism by star. Okay. Okay. Yeah. So this logarithm, it definitely contains 1, right? Logarithm. Let's use the name log. Okay. So. Okay, so maybe there's take the logarithm according to the rate derived from star. Yeah, I think the domain. So this law contains 2 things, because there's no problem that the domain of the law is just the C, like take away this ray, right? And then the second thing is that because for each of the values on the log, we need to pick what is actually the angle that we want it to sit on, right? So we fix the angle such that it maps this point. So basically, for each of the law, you have to really pick a continuous choice of the argument function for each point, right? So we pick the continuous choice of argument function such that it maps this point 1 to the point 0. Okay. Together with the restriction, this log of 1 must be mapped to 0. Okay. Okay, so okay, so now we can analyze what happens on these ANs. So okay, so now the question becomes so under this log, right? So would this log of so the sum of this log, right? Use I from 1 to infinity, log of 1 plus z over omega I converges. Okay. So okay. I think maybe they will converge because again, like when this omega I is very small, when this omega I when this index I is very small, right? It would lies outside this circle, and then when this I is large, this 1 minus z over omega I will lies inside this circle, and since the major points, right, the infinite tail parts of this sequence lies inside this circle of this very small radius. So after taking this log, so what would happen after taking this log? So after taking this log, so the points will be getting closer and closer to 1, right? So these points are getting closer and closer to 1, and also so when we take the log, okay, so when the points are getting closer and closer to 1, so when we take the log, the radius is so what happened to the radius when the point is getting closer and closer to 1? The radius must be getting closer and closer to 0, right? Because the complex log is being defined as the complex log of a complex number Ez, which is represented as r e to the I theta, right, is equal to the real log of the radius r plus I times the argument of this function. Okay, so basically when the radius is really close to 1, right, so just imagine that you take the real log of a number that's really close to 1, you will get something that's close to 0, right? So namely, like the radius part will be close to 0. Okay, so the radius part, yeah, maybe I want to be more careful. So I'll say it first. So the radius part will get closer and closer to 0. Okay, so maybe let's write down here. So the radius part, when what? Yeah, so when this I is getting, okay, so the radius part, i.e. the modulus of this guy, right? Sorry, I think I really should use minus here. Okay, so yeah, is getting close to 1 when this I is goes to infinity, so which implies that the real log, let's use this ln for the real log, right? So the real log, okay, the ln of this guy, it goes to 0. And also, I think we also have the fact, yeah, because everything, right? So the whole point is getting closer and closer to 1. Not just the radius, but the point itself is getting closer and closer to 1. Which means that the angle part of this point is also closer to 0. Okay. So okay, So and also the yeah, because yeah. So yeah, I think one way to see that is, so basically if we take the limit, yeah, so maybe let me say it here, and also yeah, let's see what is the notation that I should use in class about when we specify a branch of log. So what is the notation that we use to denote the argument part? Okay, so maybe I think this video might be too long. So yeah, so and also the angle. Okay. Okay, so I'll use the this function. I cannot really use this function. So so what function should I use? Okay, so maybe I use okay. And also the angle of I use A for the continuous choice of the argument function. That is used in this log function. Okay. Also goes to 0. Okay. Okay, so let's pause here. Okay. So but this guy, of course, this guy, of course, needs some further argument. So why this real log goes to 0 and this one? Because I think in order for us to show that, because here it's not just that the limit goes to 0, right? So of course because this point, okay, I think this is a more complicated argument. So because when we take the limit of just this sequence of point, the limit of this sequence of point will just converge to 1, right? So therefore when it converges to 1, because this log function is continuous, the limit will just converge to 0. Okay, so there's no problem about the limit convergence, but the problem is about the convergence of the series, right? So I think we need some further argument to really show the maybe like showing if we want to show the limit of the convergence of the series. So and also so let's see so log z is equal to the real log, which is we use letter ln of the modulus z plus I times az. Okay. Yeah. So this is a representation of this law. Okay. Yeah, okay. Yeah, so we shall continue next time.